Okay, welcome back. This is Steve Gibbs again. In this session, we're going to take the basic circuit that we broke down into its component parts last time and solve it using matrix algebra. Okay, here's the circuit that we are working to solve to find the currents I1 and I2. And with it, here are the two equations that we came up with in the first section. As we reorganize them to identify current 1 and current 2, our unknown vector, in terms of the resistances. Now we need to transfer that into a matrix format, AX equals B, and this is what we end up with. We have our resistors forming the matrix A. We have the unknown currents, I1 and I2, for the X vector, and we have our voltages, V1 and V2, for the result vector. Substituting numerical values in instead of the symbolic R1, R2, R3, here we have the matrix 1, 2, 1, 0, minus 390, minus 390, and 590. There's our matrix A, I1 and I2 for our unknown vector, and 4.3 and 7.9, both negative, for our result vector. So let's go back to matrix algebra for a moment. We've got AX equals B. What we need is the unknowns, so we've got the inverse of A times B. And as we've already discussed, the inverse is 1 over the determinant times the transposed matrix as shown. So moving on to find the determinant. The determinant R1 plus R2 in the A, B position minus R2, C position, D position R2 plus R3, leads to R1 plus R2 in the A position, again, minus 390, minus 390, 390 plus 200. So here is our determinant equation, which leads to AD minus BC. Gives us the value of 561,800 as the determinant of our equation. Looking at the transpose, again, we'll just swap A and D, and we negate B and C. So now this is our new transposed matrix, and the inverse becomes 1 over delta times the matrix. So we have these values, and we can linearly multiply 590 time divided by this, 390 divided by 390, and 1210, each divided by the corresponding 1 over delta. Notice also quickly, the negative signs went away because these were already negative values. So we have minus a minus 390, minus a minus 390. So double minus, and now we have pluses. Solving for our unknowns, we put the whole thing together, and it comes out surprisingly evenly for all the wild numbers we've been calculating with, that x1 is going to be minus 0.01 amps, x2 is going to be minus 0.02 amps, or I1 is equal to minus 0.01 amps, and I2 is equal to minus 0.02 amps. So here's what we came up with when we solved the problem. We found out that I1 was 0.01 amps, or 10 milliamps. I2 was 0.02 amps, or 20 milliamps. But the minus signs tell us something else. The minus signs tell us that where we had assumed the current was going clockwise in each of these loops, that in reality the current was going counterclockwise. And that's the negative sign. So do we get a good answer? Absolutely. But it's in a different direction. So for R1, the current is actually going down. And for R2, again, I2 minus I1, the 20 milliamps going in the counterclockwise says that ultimately we'll have 10 milliamps here. And finally, we have 20 milliamps going in the bottom to top position, creating a plus to minus across R3. Now come back one more time, and we're going to solve the problem the third time using Cramer's rule. See you in a few.